Um, Good day, class. So, as agreed in class, I will be sharing a voice lecture to support our classroom learning. Please note this. This is not a scheduled class and should not be treated as such. This voice lecture is only meant to complement our lessons in class. So, class attendance remains your top priority as it is essential for effective learning. Thank you so much. So we'll be looking at, I've already sent the slides of your LMS, and by now you should have gone through that. So this is just like a revision because you should have gone through the slides or the lecture notes before now. So this particular aspect of chemistry is referred to as organic chemistry, and the code is CHM 102. So we'll be looking at, first of all, the history of organic chemistry. That is how organic chemistry developed. Now, before we go to that, as a word of introduction, I also want to emphasize here that chemistry still stands out as a subject of importance to the society and for all. Chemistry, like we know, the letters that make up chemistry as a word is us. We have the C standing for community, the health, environment, the medicine. I is for industry. The S in chemistry stands for science, the T technology, the R research, and Y you. So it involves everything as far as development, as far as science, as far as humanity, as far as engineering is concerned. Now, in the aspect of chemistry that concerns us, I want to let us know that for us engineers, chemistry is actually an important fundamental topic. This is because we understand through chemistry the properties of materials. Remember, engineers, we have a lot of designs that we make in building new things like bridges, pipes, and all of that. So we need to understand the basic things in chemistry or the properties of materials that we need to use to design for a particular thing, depending on the function of that particular material. For example, you want to look at a material that you use in electricity, so you should go for something that has high electrical conductivity, and as such you will need to know which material has that property so as to know which to use. We emphasized on this the last semester, so I'm not going into details on that. Again, it helps us to understand our natural environment, the atmosphere, what is composed of, how do we combat or how do we reduce pollution and all of that. And it also helps us to understand the reaction of materials with the environment. With this, we can avoid, designing materials that can corrode easily. Now, organic chemistry in its own plays a part in the development of common household chemicals. For example, the food, the plastics, the drugs, the fuels, and all of that. And we also know that most chemicals form parts of our daily lives. That is, most of these chemicals we have mentioned, it forms part of our daily lives. Now, the history of organic chemistry can be traced back to the name organism. You know, organic came from that word organism, which means living thing. And when we talk about living things, we are referring to plants, animal, bacterium, we are referring to fungus and all of that. Now, period to 1828, most organic compounds were obtained from organism, either plants or animal or the likes, or their remains. Their remains means maybe when they decay, they decompose to give us a particular organic compound. Now then, the scientists then believed that organic compounds could only be produced within living matter, while inorganic compounds could be synthesized from non-living matter. Just check the words. organic compounds could be produced within living matter, meaning that you're producing them, you're not synthesizing them in the lab. So they are coming out from nature. Now, why inorganic compounds could be synthesized from non-living matter? So for inorganic compounds, you could actually go to the lab and synthesize your inorganic compound. That was the scientific philosophical reasoning back in the years. Now, they also have this strong belief in theory of vitalism. This theory implies that there could only be a vital force that is necessary to produce these organic compounds from living things. So if a living thing does not have a force to push the organic compound, that organic compound will not be produced. Anyway, we are going to see if this is true. Then, organic chemicals were also used in ancient times. The Romans, the Egyptians, they used organic chemicals in their dyes, their medicine. They use it as poison from natural sources. But the thing about, there are no chemical composition of those substances. If this is, let's say, for example, their chemical composition were unknown. Then in the 16th century, organic chemistry were also being used. But at this particular time, the composition of the organic compounds were actually determined. So you could know that, okay, if I isolate an organic compound from a plant or from a natural source, that I can actually go and analyze it is composed of nitrogen and clear that organic are good news. By a German scientist named Ulla Frederick. Kula made a good breaking contribution that challenged the idea of vital force. Remember, we have talked about the belief of the ancient science. Let me use that word. They believe in the theory of vitalism. Who actually challenged vital force? What did Wula do? We got to know. Now, he made a breakthrough by actually successfully synthesizing urea, an organic compound, from ammonium cyanate, an inorganic compound. This experiment proved that organic compounds can be synthesized from the lab using inorganic substances. And so you can actually get your organic compound without involvement of living organism. And so you might not involve, you will not, variably not involve the vital force. This is actually a great breakthrough because it has actually nullified, or it has actually challenged this idea of a vital force. And so scientists started synthesizing organic compounds from the laboratory. Now, this also tells us something about what we learned the last lecture. The equation is given on your slide. You can look at the equation. You have the generation of the ammonium cyanate. Actually, the ammonium cyanate is an intermediate. It's an important intermediate. If not produced, the urea, which is an organic compound, will not be synthesized. And so when the intermediate, which is ammonium cyanate, is produced via the reaction of silver cyanate and ammonium chloride, the ammonium cyanate is heated up and urea is being produced. Now, also, William also demonstrated that he actually did what we refer to as, testing his idea, that is hypothesis. He actually had other reactions that generated the important intermediate, which is ammonium cyanate. because that is also in your slide. For example, when he reacted cyanic acid and ammonia, ammonium cyanate was generated. He also reacted lead cyanate and ammonia, ammonium cyanate was also produced. And so all you need to do is heating up the ammonium cyanate to get the organic compound urea in the lab. Now, also, we have here a picture, showing us that this urea, which can also be produced by nature, can also be synthesized in the lab. So you have the organic part and, the inorganic part and the organic part. The inorganic part shows us the roots or the scheme to the synthesis of urea. Now, the organic part shows us the biological aspect. That is what the body system, how the body system produces urea, which is telling us that whatever we think is an organic compound being derived from nature, be it plants, be it animal, that scientists, in this case chemists, could actually look at or propose a mechanism or a synthetic route to the production of that particular organic compound. Usually, organic compounds isolated from nature are usually isolated in a very minute quantity, a very small quantity. And so these organic compounds being needed in large quantity are being synthesized in the lab. So the chemist will design a synthetic route to the production of the organic compound in the lab. Now, the next thing now we want to look at is how do we now define this particular organic chemistry. But before then, like I said, now other scientists started producing organic compounds. And so chemists considers organic compound as those compounds containing carbon, hydrogen, and one or more other elements. Most of these elements are hydrogen, oxygen, nitrogen, sulfur, phosphorus, sometimes halogens, and all of that. We have already looked at that in the class. So we can actually define organic chemistry as that branch of study or that branch of chemistry that deals with the synthesis, the structure, the reactivity, and the properties of carbon and its compounds, though it's not limited to only this. Now, we want to look at the properties of organic compounds. The properties of organic compounds are actually due to their carbon-hydrogen bonding. So they exhibit this unique property, both physical and biological. This unique property is attributed to their carbon-hydrogen bonding in them. These properties include one, flammability. So many organic compounds, they burn when exposed to heat or flame. And when they burn, they release energy in form of light and heat. They are also soluble in organic solvents such as ethanol, acetone, methanol, and chloroform, and other organic solvents, but they are less soluble in water. And some of them are even insoluble in water. So the solubility of organic compounds are the solubility of organic compound is much they are much soluble in organic activity. Organic compounds play essential role in this. Carbon dioxide, please, is not an organic compound. Carbon dioxide is our CO2. It is not an organic compound. Why is it not an organic compound? Carbon dioxide is not an organic compound because carbon dioxide, it lacks the carbon hydrogen atoms. That is, it lacks the hydrogen atom that is directly bonded to its carbon, What you have is oxygen directly bonded to carbon in carbon dioxide. And so, because it does not have hydrogen directly bonded to carbon in the carbon dioxide, it is not an organic compound. And again, it exhibits the physical and chemical properties that is more consistent with inorganic compounds. Though it's also not an inorganic compound, but it's closer to inorganic compound than organic compound. So because carbon dioxide does not have hydrogen atom directly bonded to its carbon, it is not an organic compound. It again does not exhibit the general properties of organic compound. For example, we say that organic compounds are flammable. Carbon dioxide is a non-flammable gas. We say that organic compounds are less soluble in water. Carbon dioxide dissolves readily in water. You could see that it has a different property compared to the organic compound. And so carbon dioxide is not considered an organic compound. Now we have other examples of inorganic compounds that people, because they have carbon molecules in them or carbon molecule, people assume that they are organic compounds, but they are not. For example, you have carbon monoxide, you have sodium bicarbonate, and you have iron cyanide. All of these, though they contain carbon, they are not organic compounds. We also have compounds that contain elemental carbon. These compounds are also not organic compounds. For example, and these compounds, for example, you have the amorphous carbon. Amorphous carbon is not an organic compound because it contains only carbon atoms. Then you have your fullerene. Fullerene is not an organic compound because it contains only carbon atoms. It does not contain carbon hydrogen bond, or neither does it contain carbon bonded to another atom. As a matter of fact, fullerene contains 60 carbon atoms. We'll be looking at fullerene and its application as a subtitle in today's class. Now, these elemental carbons are actually referred to as allotropes. We are going to be looking at that shortly. But let us quickly look at the general characteristics of organic compounds. Remember, we've actually looked at their unique properties in terms of their flammability, in terms of their solubility in organic solvents, and their role in biological activity. The general characteristics of organic compound is that it can be isolated as well as prepared in the laboratory. For example, we've seen that the way urea is being produced in the body system and the way it is being synthesized in the lab. Now, these organic compounds, they also possess complex structures and they have high molecular weights. Their properties are decided by certain active atom or group of atoms known as functional group. We are going to be discussing functional group again in this class. They are mostly insoluble in water, but soluble in organic solvents, and they are combustible in nature. So these are some of its general characteristics. Now, talking about organic compounds, talking about organic chemistry, like I said earlier, that organic chemistry could be referred to as chemistry of carbon. What is it that is in this carbon that is making it so special, as having the name chemistry of carbon? Now, and why are we now devoting this special branch of chemistry, to the study of carbon instead of chemistry of carbon? So let's look at the uniqueness of carbon. The uniqueness of carbon atom stems from its catenation ability. What is catenation ability? Catenation ability is just that carbon has the ability to combine with one another, that is to combine with carbon. It can combine with another carbon, and it also has the ability to combine with other atoms through covalent bonding to form chains. This is referred to as catenation. So this ability of carbon to combine with itself or combine with other atoms through covalent bonding to form chains make carbon-containing compounds to be great. You have a lot of carbon-containing compounds. And also, because the carbon-carbon bonds are much stronger than the bonds between any other two atoms of the same element, say chlorine bonded to a chlorine atom, the bond between the carbon-carbon atom is stronger than that of chlorine-chlorine atom, and so they are very, very stable. They do not dissociate or break up easily like the other atoms combining together. Now, again, the carbon-carbon bonds are stronger than carbon-fluorine bond, carbon-oxygen bond, carbon-nitrogen bond. And so this is also what is giving them that particular ability to form a great number of carbon-containing compounds. So again, like I said in the definition, that when they catenate, they form compounds in chains, that can be in rings, that can be in spheres, or they can have them in tube form. Now, when carbon reacts with itself, not reacting with another atom, you have several atoms, maybe 100 atoms of carbon coming together to react with itself. Like we said, they are not organic compounds, but they are special group that we have to treat, in this particular course, because we are looking at the chemistry of carbon. And so because they involve just carbon atoms, it is ideal that we discuss them here. It's just better that we discuss them here than discussing them under the inorganic aspect. So these compounds are this particular group of compounds are referred to as allotropes. So when you talk about allotropes, you're talking about an element that exists in two or more different forms, but in the same physical state. Listen, take note. It exists in elements existing in two or more different forms, but in the same physical state. Remember, when we talk about physical states, we are not talking about physical properties. We are referring to the physical states such as the boiling point, the melting point, the color, not when we talk about the physical state, we are talking about the solid, the liquid, and the gas, not physical properties like boiling point, melting point, and color. So that you should know that allotropes, they have the same physical states, but they don't have the same physical properties. Now, what examples of these allotropes of carbons are? You have the diamond, you have the graphite, you have the coal, you have the fullerene, you have amorphous carbon, and so on and so forth. You have the diamond. So those are allotropes of carbon. We'll be taking them one after the other, but our emphasis is going to be on fullerene. So I'm going to go to fullerene so that we'll discuss the fullerene and its application. Now you can read up the rest, the diamonds and the diamond, the graphite, the amorphous carbon, and the others. Now, fullerene, it's spherical. What we mean by spherical is that it has a spherical shape. It is called a buckyball. This buckyball is as a result of this shape that it has. You also have the cylindrical ones that are referred to as the nanotubes. And the fullerene is actually composed of carbon atoms. It is entirely made up of carbon atoms arranged in a series of interconnected hexagons and pentagons. There are no other atoms in fullerene except carbon atom. As a matter of fact, fullerene consists of 60 carbon atoms. Now, these fullerenes are produced through artificial means in the laboratories, using techniques like laser vaporization of graphite or chemical vapor deposition. So these are the ways you can actually prepare them in the lab. And with this method, it allows, remember we said, in understanding chemistry, we could actually understand the properties of materials and how the reactions, how we can manipulate them to get whatever we want. This method now allow these methods, because you have two methods, laser vaporization of graphite or chemical vapor deposition. It allows scientists to control the size and structure of fullerene molecules, depending on what their application is. If they are meant to be used in nanotechnology, they will be designed in such a way to fit into that particular application. If they are meant to be used in medicine as in drug delivery, they will be designed in such way, or in material science, they will be designed in such way. So these methods allow us to actually play around the size of and the structure of the fullerene. Now, the applications of fullerene. One is that fullerene molecules, they are used for drug delivery into the body. They are also used as lubricants. They are used as catalysts and in the form of nanotubes for reinforcing composite materials, such as our sports equipment, like the tennis rackets. So you use them for drug delivery in the body, use them as lubricants, and use them as a catalyst, and they are used in the form of the carbon nanotubes. They also have chemical and pharmaceutical applications. Like we said, they are used in drug delivery. Then the chemical derivatives of fullerene, they have a fascinating complex electrical and magnetic property. So they can be used as electrical and the material property of a particular compound. Now, when we talk about plastic, food, textiles, and dyes, you have many of these being used there. So the next thing that I want to look at is classification of organic compounds. Basically, organic compounds are classified into two broad categories. One is the classification based on structure, and the other one is classification based on solubility. For this class, we are going to be concentrating on classification based on structure. So the classification based on structure, organic compounds are classified either as aliphatic or aromatic compounds. Now, under aliphatic compounds, organic compounds are also classified as cyclic or acyclic. When you talk about acyclic, we are talking about straight chain or branch chain organic compounds. Now, for aromatic, we know that aromatics are cyclic, so there's no way about talking on any other thing. Now, for the aliphatic compounds, aliphatic organic compounds could either be saturated or unsaturated. Saturated means when you have the single bonded organic compounds. Then unsaturated is when you have the double or the triple bonded or aliphatic organic compounds. Now, we have over 3 million organic compounds that has been prepared in the laboratory. Now, more than 3 million anyway. How do you now start naming these compounds? How do you differentiate one from the other? If you have as many of these organic compounds being produced in the lab, how do you differentiate one from the other? There is a good news. Organic compounds exist in different groups whose properties are very similar to one another, but they differ from other groups. What this means is that you have a particular set of organic compounds, say maybe 500,000. I'm just making an exaggeration. I'm not sure, but just you should look at it that way. Maybe 500 that has the same group in them, which is different from another 500 own, another 200 own. So you can actually distinguish each category from the other. Let's say we call them group A, group B, group C, group D, and so on and so forth. You can actually differentiate group A from B, because group A, all the organic compounds in group A have a common feature in them, or have a common group of atoms or atoms in it that makes it differ from B. So once you see A, you know, oh, this one is in A because it has this, or this one is in B because it has this particular group of atoms. Now, each of these atoms, they have distinct structural feature, which is responsible for their physical and chemical properties. And as such, they are classified based on this. This specific group of atoms or bonds within an organic compound that is responsible for giving it a unique or its unique physical and chemical property is referred to as functional group. We'll be looking at functional groups. So these functional groups, they play a significant role in directing or controlling organic reactions. In fact, the functional group gives distinctive property to organic compounds. So depending on the functional group an organic compound contains, it directs its reaction or its property, chemical properties. Here we have, okay, I'm going to be stopping this share to look at some organic compounds. I mean, some functional groups. Okay, let's look at this slide. We have this group called the carboxylic acid. What makes a carboxylic acid is the presence of this particular group, the COOH group. That is what makes this different from the next. So I can actually, once I see that a compound has this group of atoms in it, I will say, okay, this compound is an acid. If again, you have a compound that has this particular group, the carbon-oxygen double bond with a hydrogen attached to the carbon that has the oxygen atom, that is an aldehyde. So this makes this particular group different from the other groups. Then we go to the next one, which is a ketone. You could see that a ketone has a carbon-oxygen double bond, but the carbon that has the oxygen is not, there's no hydrogen atom attached to that carbon. So that makes it different from the aldehyde. Now you have your amide. This is the functional group for an amide. The carbon that has the oxygen, the carbon bonded to oxygen double bond has a nitrogen atom attached to it. So that makes it an amide. Now you have your alkene, the double bond, your alkyne, the triple bond. You have the ether. You could see that ether has an oxygen with a single bond to a carbon atom on each side. Then the alcohol has the OH group. So this particular group that we have identified now is what is making each of these group of compounds to be different from the other, so that you cannot actually classify an aldehyde as a carboxylic acid, because an aldehyde has a hydrogen atom directly attached to the carbon carrying the oxygen atom, but here is a hydroxy group OH that is directly attached to the carbon having the oxygen atom for carboxylic acid. So they have distinct structural feature. None resemble the other. They are not the same. And that is what functional group is all about. So you have group of compounds having, they have the same specific group of atoms or bond that actually defines their chemical or their physical reaction. So the next thing that we want to look at in this class, before I end this class, remember I told us we actually have this class, we have had this class. I'm just making this video to further, help us in our study, to aid us when we actually, when we are reading the slides, or when we are going through the slides. We have another important term or terminology that I want to discuss under organic compounds. We have what we call the homologous series. The homologous series. The homologous series are compounds that belong to a class of organic compounds that differ from one another by a multiple of CH2 units. They differ by CH2 units. So these are compounds. They are organic compounds. They belong to the same class of organic compounds, but they differ from one another by CH2 units. Now, what this means is that as the number of CH2 increases, that is subunit increases, there's you actually know that the physical properties such as the boiling point and the melting point and the solubility, they will actually differ from one member to another because there is increase in the molecular weight as you go down the group. Now, one thing you should know about homologous series is that they have similar chemical properties because they have the same functional group. But what differ in them is that they just differ by their what? The additional CH2 group that is added to them. But for these compounds, they exhibit similar chemical properties. I have an example here to show. If you look at this for alkane, these are for homologous series because each differ by a factor of CH2. Oh, this is CH4, sorry. This is CH4, please. This is CH4, that is your methane. This is C2H6. This is C3H8. Please kindly correct that CH4. Now, alkane again for the homologous series because each one differ by the other by CH2 units. And again, alkyne differ because each one by the other by CH2 units. So that is what homologous series is all about. Compounds with similar chemical properties but differ from one another by additional CH2 units or CH2 group. Now, like I said, that every member differ from the other by CH2 unit or CH2 group, meaning that they differ by a relative mass of 14. Remember that your carbon is 12, your hydrogen there is 2, 12 plus 2 is 14. So if somebody even asks you that, what do you understand when you have two compounds in the same class, but their relative masses differ, the relative masses of one differ by the other by 14. It's just asking you about homologous series. Again, remember, members of the same homologous series, they can be prepared by one common method. Why? They exhibit similar chemical properties. Now, we already emphasized that they have the same chemical properties, and so there is an example here in your slide where you have the reaction of ethylene and methane with bromine. Now, ethylene is an alkene with a 2 double bond. While you have methane is a complex alkene. But the thing here is, if you look at that structure, you could see that the center of attraction is that point where you have the carbon-carbon double bond. Whatever you have, whatever structure you have is not important as far as the reaction is concerned, because reaction takes place at the point where you have the functional group. You could have the number of atoms from here to 1 million. The interest of the reacting agent is to, the agent will be looking for the functional group. Where is the functional group? Because it's at that point that it will act. It cannot act in any other point except the functional group. So that is why, even though alkene looks smaller than the other complex compound, still the bromination is on the 2 carbon that has the double bond. So that is where you have the bromine attacked. The bromine attacked those 2 places. So I believe that what this is telling us is that it does not matter the size or the complexity or the complex nature of any organic compound. What determines the reaction of any organic compound is the functional group. So it is where the functional group is that reaction takes place. So every other thing in that compound, be it a complex compound, be it a small compound, is not important as far as that reaction is concerned. They will still come as they were. There won't be any change in them because there's no reaction on them. So reaction takes place where there is functional group. And in this particular case, we know that the functional group is on those 2 carbons having the double bond. So with this, I'm ending the first class, and I hope this will help us with what we have in class, with what we have learned in class, and what we have read from other textbooks. Thank you so much, and expect the second video shortly. Thank you.